go. Okie dokie. So here we go. Okay, as I said before, welcome to this webinar. Today we're going to talk about product integration with emphasis on delay integration. But before we do this, I thought it might be a good beginning to briefly explain the Zoom platform that we're using. So all of you are expected to see a window not unlike the one that you see here. In the bottom of this window, you will have several buttons that allow you, for example, to unmute your microphone or to start your video so that we can see you. And in addition to that, there is a button that is called Participants. If you click that button, a window will open to the right, and then you will see all your fellow attendees that are joining today's meeting. There is the possibility in the right-hand window to raise your hand. This is a convenient way for letting me know that you want to ask a question, because this is not going to be a monologue as far as I'm concerned. This is going to be a dialogue. And that means that if you have a question, if I am not expressing myself clearly, by all means, raise your hand, let me know, and I will try to address your question to the best of my abilities. After that, I will typically lower your hand so that we know that your question has been answered. In the bottom of the screen, you also have a chat button, and if you click the chat button, another window will open up and it will show a chat. And this speaks pretty much for itself. You can address the nation by typing a message in the box at the bottom, which will go to everyone. Or if you happen to see a friend or a fellow colleague in the participants, then you can also address a message to that person in private. What I will do is, because I expect people to sign up during the course of this webinar, and that means that I will mute all your microphones regularly to keep the transmission lines as clear as possible. Does that introduction suffice? Does allow us to move forward? Okay, somebody says yes. Great. So as I said before, we are gonna talk about product integration. So let me go back to sharing my screen once more and see what we are gonna discuss. Okay, product integration is a feature that is available on Galileo Galaxy devices and requires Compass 4.6 or later. Because in product integration, we basically consolidated two features that already existed in previous versions of Compass, which is the so-called delay integration, which is today's focus, and is all about making sure that the loudspeakers that we use out of the Meyer sound inventory are phase compliant, that they have the same phase response and will play nice together. In the past, we would also have EQ starting points, and they have also been relocated to the product integration feature, and that will be covered in another webinar. Where delay integration is about making sure that the loudspeakers play nice together, have the same phase response, the EQ starting points have the same function, but it's not about phase compatibility, but rather about amplitude compatibility. And we'll discuss that in another webinar. What we'll discuss today is phase curve naming convention. How do we identify phase curves, and how do we name the families of phase curves that you will find in a Meyer sound ecosystem? We have to answer an important question, which is who is in control, who is in charge? Is amplitude in control or level, or is phase in control, as we're about to discover? I'm going to follow up with a demonstration in MAPP XT showing you to use product integration with emphasis on delay integration. and I'm gonna explain to you when it's time to obsess about phase compliance or not, because there are certain instances where phase compliance is mission critical, whereas in other instances it is not mission critical. Okay, so then we'll continue with propagation delay, because delay integration as part of product integration will make sure that the loudspeakers become phase compliant, but it doesn't address the internal propagation delay inherent to the different loudspeakers in the Meyer sound portfolio. So that is also something that we have to be mindful of. And finally, a demonstration in Compass for a mixed array consisting of Leo and Lion elements. So there we go. Phase curve naming convention. Over here we see a screenshot from MAPP, and we see a phase response, and in the center of the screen there is a phenomenon that we refer to as a wraparound or a phase wrap. Should you encounter this phase response in the wild, how would you label it? How would you name it according to our naming convention? Well, it goes in the following fashion. You scan the plot, you scan the chart from right to left, and then at one point you see the line leaving the chart, and at that very frequency where the wraparound lives, where the phase wrap occurs, that frequency in this particular instance happens to be 500 Hertz, and we would then refer to this phase response as PC 500, which informs me that the first wraparound coming from the right, going down in frequency to the left, that the first wraparound occurs at 500 Hertz. And from here on, we will refer to that as PC 500. Does anyone have a question regarding this naming convention at this point? Okay, well, let's look at some of those. Okay, I see a possible chat coming up, and let me see, all clear. Well, that is awesome. Thank you very much. Meyer Sound is always trying to improve the native phase response. That being said, of all the products in our portfolio, you could categorize them basically in 3 classes or in 3 phase curve families if you want. This is not all loudspeakers in our inventory. This is mostly the loudspeakers that are being used in touring sound and installation work, but this is a vast majority of the products in the Meyer Sound portfolio. And the bulk of them, such as Leo, UPQ, UPA, UP Junior, UPM, all of those loudspeakers have a phase curve that lives roughly around 125 Hertz. And we call that family of phase curves, we refer to that as PC125. That being said, as we're continuously trying to improve the native phase response of our products, these phase curves have been subject to change let me briefly mute a microphone. Okay, so. Okay. So I've managed to make a window disappear. Story of my life. Microphone has been muted from what I can tell. Great. Okay, so let's continue with the presentation. Okay, so I talked about the green phase curves, which are all part of a family which we call PC125. They live roughly around 125 Hertz. That's where we see the first rep. However, as we're trying to improve the native phase response of our products, things are subject to change, and that means that if you look at current generation products such as Lena, UPQ D1, Ultra X40, Ultra X20, but also Leopard and Lion, they have the wraparound or the phase rep living at a different frequency, and that is typically between 55 and 70 Hertz. So we refer to that as PC 55, 70 Hertz. That's another family of similar phase curves. However, that being said, there's a third family that we can refer to, and that is the so-called M-series products such as Milo, Mike, and Melody. And they have their first wraparound living around 350 Hertz, and we refer to that family of phase curves as PC350. And those are generally the three major families of curves that you will find in a Meyer sound ecosystem. However, it also sets the table for these loudspeakers not being able to play nice with each other out of the gate. And that is something that delay integration as part of product integration solves with a few mouse clicks. Any questions so far? I see a question regarding M1D. I'm not prepared to answer that question at this point. That being said, there's nothing that keeps you from investigating this in MAPP because that's how I collected this data. So that question, that remains to be seen. Okay. Why is phase compliance important? Well, in order to understand that better, we need to look at what happens if we start combining several loudspeakers from different phase curves. Or I should say family of phase curves. In the corner of my eye, I see a question why UPQ is in both categories, because there is a UPQ 1P and there's the successor of the UPQ 1P, which is the UPQ D1, and those will be the loudspeakers that I'll end up using in the MAPP demonstration that we're about to see. But in order to appreciate the importance of matching phase curves for loudspeakers from different families, we first have to see a little bit more examples. For example, here we see the native response of a Lion, a Leo, and a Milo loudspeaker. And notice that for a Lion loudspeaker, that wraparound lives between 55 and 70 Hertz, whereas for a Leo M loudspeaker, that wraparound lives at 100 Hertz. We call that PC100. And for Milo, as we already saw before, that wraparound lives at 350 Hertz. However, once you resort to delay integration as part of product integration, then suddenly we can make it happen that all these loudspeakers feature the wraparound at the same frequency. So with help of delay integration, suddenly these loudspeakers all feature their wraparound living at 125 Hertz. And that means that these loudspeakers, when they encounter each other in the audience, in the venue, in the listening space, when they come together, they will play nice for all frequencies and not just for certain frequencies. And in order to investigate that a little bit more in depth, we are gonna look at a practical example. But we need to first understand why phase matters and when it matters. And that means that we first need to investigate who is in control, amplitude or phase. And in order to demonstrate that, I'm gonna switch to a different application. I'm gonna attempt at making you hear what will happen. So I'm temporarily going to stop sharing my screen. I'm going to share my screen once more, but this time with audio. This is always a little bit tricky to share the computer sound, but hey, let's see what happens. So I'm going to quit the PowerPoint and I'm going to go to a digital audio workstation. And you should be able to see that digital audio workstation, provided that I share my screen. Okay, there we go. Can you confirm that when I hit play that you hear big noise? So everybody hears the big noise. Excellent. So here's what we're gonna do. In track A, we have pink noise, and I'm gonna make a duplicate of that pink noise by clicking the waveform, by copying the waveform in a second track. So now we have two instances of the same waveform. I'm gonna turn the level a little bit down because I'm a little bit loud. So this is the level of one pink noise. And if I turn on both channels, then in coherent summation, you would expect to see 6 dB increase in level. No surprises here. If you look at the bottom left corner, you will see that the level goes from roughly -12 -6 whenever I turn on 2 channels at once. So, what if there's a phase offset? What if there's a 180-degree phase offset for all frequencies? Then summation becomes cancellation. Not today. This is Merlin's Law. Everybody calls it Murphy's Law. I don't know who Murphy is. I call it Merlin's Law. So let's try that again. Okay. 2 tracks. And if I flip the polarity, then addition becomes subtraction. And because my levels are matching, I get perfect silence. Without the polarity reversal, perfect cancellation. Without the polarity reversal, perfect cancellation. Provided your levels are matched. So what happens if we attenuate one copy of the pink noise? Summation evidently drops. But see what happens if we now flip the polarity, introducing a 180-degree phase shift for all frequencies. Suddenly, toggling the polarity reversal doesn't have the same dramatic effect as it had before, because there's a 20-degree level difference. Whereas if we equally loud, flipping the polarity is like on or off, on or off. So the larger the level offset, the less of a chance phase offsets have to wreak havoc on the summation. However, if level approaches each other, right now we have a 5-degree level difference, then the polarity reversal becomes more powerful. So that's a very cute example how you can demonstrate what happens if you have matched levels but are out of phase, in this case with help of a polarity reversal. So if I were to ask you who is in control, amplitude or phase, then it's safe to say that amplitude is control. If there's a level discrepancy, if one source is substantially louder than the other source, amplitude is in control. However, if your levels match, then phase becomes a tiebreaker and makes the difference between summation or losing everything. So if we want to talk about when is phase compliance important, then we can draw the following conclusion. When your levels are matched, it is mission critical that you are phase compliant. However, if you are separated by 10, 20, 30 decibels, then having a mismatch in phase, having a phase offset becomes negligible, becomes trivial. Any questions so far? Okay. Let's look at an example. And for this example, I will use 2 loudspeakers, which basically the UPQ-D1 is the successor of the UPQ-1P. They have the same dimensions, exterior dimensions, but the UPQ-D1 is next generation and makes use of technology that we learned from Leo family's product and more. Not to mention that the UPQ-D1 has a phase curve which is 55-70, whereas the UPQ-1P, as we're about to discover, has a phase curve which lives at 100, and it remains to be seen what happens if we start combining these 2 loudspeakers without correcting the phase response with help of delay integration as part of product integration. So let's go to MAPP. MAPP is our proprietary prediction software, which you can download for free at the website. And if everything goes accordingly, you should see 2 loudspeakers living on top of each other. I wrote a big D over here to remind me that that is the UPQ-D. And I wrote a big P over here to remind me that that is the UPQ-P. The D, as we're about to discover, is PC 5570, whereas the P, as we're about to discover, is going to be PC 100. If I zoom in on the loudspeakers, then you will see that I've tried to bring these loudspeakers physically as close to each other as is possible. We have the horn of the UPQ-D living in the bottom, whereas the horn of the UPQ-P living in the top. And in the median plane, the line that lives between both loudspeakers, I've dropped a microphone at a distance of roughly 10 meters. And now we're going to make some measurements using virtual sim in the MAPP prediction software and see what happens. So why don't we start with selecting our UPQ P and make a picture of this loudspeaker, and more important, let's look at a transfer function. So there we go, and here we see the transfer function, and let's set our delay first. So this is the magnitude response in the top, which shows you amplitude over frequency, and in the bottom we have the phase response, which shows you time expressed in degrees phase over frequency. And as you can see, around 100 Hertz for a UPQ-P, there lives the wraparound. So let's store this trace and recall it in one of our memory slots. This is the UPQ P native. Okay, and I'm going to put that in memory slot A, and now we're going to take a picture of our UPQ-D, which is the successor of the UPQ-P, and see whether my suspicion comes true. So now I'm going to choose the D, make a picture of the D loudspeaker, and see what we're dealing with. For starters, those that are capable of reading a phase trace immediately can tell that this loudspeaker is late because the UPQ-D uses newer technology and therefore results in a slightly longer internal propagation delay in the loudspeaker. So we'll address that later, but we're going to set our delay finder once more. And notice that at this point, we can tell that our UPQ-D, which is the blue trace, has its wraparound live between 55 and 70 Hertz, whereas the UPQ-P, as we already discussed earlier, has its wraparound live at 100 Hertz. So let's store this picture as well and call it the, let's call this guy, okay, let's call this guy, put this guy in the B bank memory slot. Okay, so okay, let's try to capture that once more. Okay, store, and let's put that in the B slot. Because now the question becomes, what happens if we now turn on both loudspeakers together? Will they sum for all frequencies? Not to mention that their levels are not perfectly matching. One of the nice things of the UPQ-1D is that it's about 1.5 dB more powerful. So why don't we fix that first by going to our Galaxy processor, and notice that the UPQ-D lives on channel 2 and the UPQ-P lives on channel 1. So let's attenuate the UPQ-D, which is a little bit more powerful. Let's attenuate that loudspeaker and capture another picture. Okay. So let's store this one and put it in memory slot B as well, or override it. Okay, so now we can see that those levels are more matched, better matched. We've taken into account the 1.5 dB level discrepancy. And now the question becomes, what happens if we turn on these loudspeakers together? Because I feel comfortable at claiming that these loudspeakers are in phase for all frequencies above 1 kilohertz. Above 1 kilohertz, these loudspeakers are phase compliant, because if we look at the phase response of both loudspeakers, then they are in perfectly good agreement. Their levels are also matched, so surely if we turn on these loudspeakers together, we expect to have coherent summation and expect to see a 6 dB increase in level. Whether that is also true for lower frequencies remains to be seen, because at lower frequencies we are not phase compliant. And if I bring up Pixel Stick, which should be visible somewhere, let's bring in Pixel Stick, there we go, and I set Pixel Stick to a 180 degree yardstick, so I make Pixel Stick 180 degrees tall, then you can tell that in the current situation that roughly below 125 Hertz, these two loudspeakers are not in phase, but they are out of phase. Everywhere we look at these frequencies, so roughly below 125 Hertz, these traces are separated by 180 degrees. And as you're well aware, when you're separated by 180 degrees, rather than getting summation, we're going to experience cancellation. So let's see whether our prediction comes true. We're going to select both loudspeakers, do another prediction, and let's see the sum of both loudspeakers together. Okay, what else is going wrong? I see a comb filter. So clearly I did not correct for the difference in arrival time. And I have a friend that is mentioning that on the chat, rightfully so, good catch. So let's address that first. Now, how can I figure this out? If we look in the bottom right corner, then we see the flight time, the time that it took for the loudspeaker for its sound to cross the distance between the source and the microphone. And the UPQP arrived after 30.1 milliseconds, whereas the UPQD, which has a slightly larger internal propagation delay, arrived after 32.77 milliseconds. So there's a time offset. So let's bring up a calculator and address that first. Okay, there's the calculator. So our UPQD arrives after 32.77 milliseconds, whereas the UPQ1P arrives after only 30.1 seconds, and that means milliseconds, and that means that the UPQP is leading by 2.67 milliseconds. So let's bring up the virtual galaxy and introduce those 2.67 milliseconds in the leading UPQP, and let's see whether we get it right this time. So there we go. Let's predict this once more. Okay, and now you see that our fear becomes reality, because as was promised, above 1 kilohertz, we see that we have 6 decibels of summation for all frequencies where the horn is in charge. However, in the portion where we predicted that our loudspeakers are not phase compliant because we haven't resorted to delay integration yet, we can see that the summation is rolling off and we actually see destructive interference. So, since everyone is a member of the SPL Preservation Society, it's safe to say that this is typically undesired, this loss of summation. However, it can also be remedied by resorting to delay integration as part of product integration. Okay, so let's try to fix this by using delay integration. I bring up the virtual galaxy and I go to the channel number 1, which has my UPQP, and I go to the portion which says delay integration. And if I click on the delay integration, a window opens up and it shows all loudspeakers from the Meyer sound inventory. In this case, we are using the UPQP. So I'm going to go to the UPQP in the list, which lives over here, the UPQP, and it gives me the option to choose from 2 available phase curves. We already know that the UPQP is not capable of the PC55 to 70 phase curve, but it does offer the PC100, which is its native phase curve, or the PC125. And with delay integration, it's always recommended to choose the lowest common PC curve available for the loudspeakers that you're using on a given day. So we're going to set this to PC100. Now I go to channel 2 of our virtual galaxy device, and I'm going to go to the list, but rather than choosing a UPQP, we're going to choose a UPQD. And of course the UPQD, unlike the UPQP, in addition to PC5570, which is its native response, also offers PC100 and PC125. So we're going to choose PC100 and we're going to click OK. And that should take care of the difference in phase curves, because these 2 loudspeakers come from different phase curves families. So let's see whether this improves the situation. Let's capture our UPQP once more, this time with delay integration activated, and get another picture. Okay, so this is the new situation. This is the UPQP. Of course, it hasn't changed because it used to be PC100 and it still remains PC100. So let me give that another name. Let's store this trace and call this the UPQP with DI as in delay integration and put that in memory bank 1. Now I'm curious to see the UPQD with delay integration this time. So we're going to select the UPQD. We're going to do another picture. And let's see what we have now. And notice that this time around, that our UPQ, that the UPQ with delay integration, UPQD with delay integration set to PC 100, notice that this time its phase response, unlike before, its phase response matches that of the UPQ1P. And that means that if we sum these two loudspeakers together, not only do we now expect to be phase compliant for 1 kilohertz and up, which we already were, but notice that we're now also phase compliant for the remainder of the audible spectrum as well, because the wraparound for both loudspeakers, although they come from different phase curve families with help of delay integration, now feature that wraparound at the same frequency. So let's see what happens if we sum them together this time by selecting both loudspeakers at once and see whether we now have success, including at the low frequencies. And lo and behold, unlike before, not only do we have 6 decibels of summation for all frequencies above 1 kilohertz, we now also have 6 decibels of summation for all frequencies at 125 hertz, unlike before. So with a few mouse clicks, I was able to resolve the situation. Which brings us to the question, when does this matter? So let's stick to these loudspeakers. Apologies, I did not intend to stop sharing my screen. Let's stick to these loudspeakers and deploy them in a common configuration. So I'm going to hide the loudspeakers as we currently see them, and I'm going to deploy them in a slightly different fashion. The configuration that we have over here is known as a coupled point source. We have one loudspeaker that is sole custodian over this part of the audience, and we have another loudspeaker that is sole custodian over this part in the audience. And together we have, in a joint effort, we have increased the overall coverage with both loudspeakers in a team effort. So one loudspeaker, like before, is a UPQD, and the other loudspeaker, like before, is a UPQP. And together they give us about 170 degrees of combined coverage. But we know that these loudspeakers out of the box are not phase compliant. And as we saw from previous measurements, we also know that they are not phase compliant out of the gate at frequencies around 125 hertz. So let's see what happens if we turn on both loudspeakers at 125 hertz, where we know these loudspeakers not to be phase compliant. Oops, I think it's safe to say that what we have over here is undesirable. Remind ourselves, this is the combined coverage of both loudspeakers together. But over here we have this huge null because these loudspeakers out of the gate don't play nice with each other. They might play nice once you make it into the custody of the horn. They might play nice once you make it into the custody of the horn, but they don't play nice at low frequencies until the mismatch in phase curve has been addressed with help of delay integration. So now that we took note of the settings, let's go to our processor. In this exercise, the UPQP once more lives in channel 1, the UPQD once more lives in channel 2. I've already attenuated the level of the UPQD to account for it being slightly more powerful, and the 2.66 milliseconds has also been introduced. And the only thing that is left to do is go to my delay integration, choose the model, which happens to be UPQ1P in this case. Choose the model, choose the lowest common PC curve available, or phase curve if you will. Do the same thing for the other loudspeaker model. Choose its lowest common phase curve, which is the UPQD, also PC100, and that should resolve the situation. Let's look once more at 125 Hz, and with a little luck, that huge cancel in the combined coverage of that coupled point source should now be resolved. And I think it's safe to say that this is a major improvement over the previous scenario, because now we have summation for all spectators within the combined coverage of this coupled point source, which still does not address the when. When should you resort to delay integration? Okay, somebody rose his hand. Go for Kalen. In this case, you have to stick with the 2.66 milliseconds, indeed, because like I said before, delay integration will make your loudspeakers phase compatible, but it does not account for the different propagation delay inherent to the loudspeakers. So that is a chore that you still have to do. Does that answer your question, Kellen? Okay. So when does it matter? When is phase compliant mission critical? Well, that is a very easy question. Phase compliance is mission critical when you're in the joint custody of one or more loudspeakers. And how can we show that we are in the joint custody? Well, let's select a single loudspeaker and look at its result at 125 Hz. At 125 Hz, I think it's safe to say that one of these loudspeakers is essentially omnidirectional. And that means that this loudspeaker is incapable of remaining in its corner. It cannot stay away from here. It cannot stay away from here, because if you're omnidirectional, you are immune to rotation. And that means that this loudspeaker is incapable of remaining out of the other loudspeaker's territory. Let's see whether this is also true for the UPQ1P. Well, what do you know? It's also omnidirectional. For a very simple reason, that at 125 Hz, we are looking at frequencies whose wavelength are much, much larger than the loudspeaker itself, and then loudspeakers tend to become omnidirectional. So like the UPQD, the UPQP is not capable of staying out of the other guy's territory, and vice versa. And that means that within the combined coverage angle of our coupled point source, everybody is in the joint custody of both loudspeakers. Everywhere you go, at all times, you're listening to both loudspeakers at nearly identical levels. And as we saw earlier in this webinar, if your levels are matching, phase compliance becomes, or phase becomes, the tiebreaker and determines whether everything is lost or everything is preserved. So that is something to be mindful of. Now, what kind of scenarios can you think of? This loudspeaker could be a main loudspeaker, and this loudspeaker could be an outfill. That would be a possible scenario. It could also be that one loudspeaker is pointing at the balcony and the other loudspeaker is pointing at the people downstairs. And I see on the chat that at high frequencies, there should not be any shared custody, because at low frequencies there's shared custody. So let me show you that for high frequencies this does not apply, provided I choose one loudspeaker. If I only choose one loudspeaker, then at 4 kilohertz we can say that this loudspeaker is perfectly capable to remaining in its corner of the room. It stays within its intended coverage and it does not cross into the other guy's territory. And of course, since these loudspeakers are ancestors or siblings of each other, if we were to look at the horn of the other loudspeaker, you would expect to see that it's capable of staying out of the other guy's territory. Sure, at 4 kilohertz, but not at 125. And at 125 hertz, that is where these loudspeakers are not phase compliant. So it matters when sources are closely spaced together, live in close proximity to each other. So that being said, let's go back to the presentation and look at a couple of scenarios when phase compliance matters. And that is, as I said before, it matters when you're dealing with sources that live in close proximity with each other. On the left-hand side, we see an outfill scenario with Leo main PA Lion outfill. And in such a scenario, it would be very much advised to use delay integration if you want to avoid the problems that we just saw with our UPQs. Another common example is the downfill. On the right-hand side, we see Leo families. We see Leo boxes in the top, and then we see 4 line boxes as downfill. It speaks for itself that in this instance, you want to be phase compatible. You want to have the same phase curve from the same phase curve family. On the right-hand side, there is an additional thing to be mindful of, because the Leo and the Lion loudspeaker do not have the same internal propagation delay. So to finish this webinar, we're going to look at Compass and how you would introduce these settings in our control software. Over here you see the overview screen in our Compass control software. I've created a situation where we have 10 Leo loudspeakers living on top of 2 Lion loudspeakers. In order to make this work, I need to make sure that these loudspeakers that come from different phase curve families, that they feature the same phase curve. And the way to do that is to select our Lion loudspeakers, go to the portion that says delay integration, which lives over here, or product integration as it's known. And then if we go and click on any of these boxes, a dialog will open. This is the dialog that you saw earlier in the presentation. A dialog will open. In this case, we choose our Lion element, and then we have several options to choose from: PC100, PC125, or PC5570, which is his native phase curve. Let's choose the PC100 and say OK. And now we need to make sure that the Leo loudspeakers that live on top of the Lion loudspeakers also use the same PC curve. So we go to the Leo M, we make sure that we choose the same PC curve, but watch what happens if I now press OK. The moment I press OK, a dialog pops up informing us that if this is a mixed Leo-Lion array, that we should add 8.05 milliseconds to all Leo M outputs. And the reason for this is that the propagation delay in a Lion loudspeaker is different from the propagation delay inherent to a Leo loudspeaker. So if this is intended to be flown as a single array, this is of course mission critical. However, if we click yes, then the 8.05 milliseconds will automatically be assigned to all Leo outputs, and now the array will work perfectly. So that is the extra step. Being mindful of the latency to account, the delay to account for the propagation delay when you're dealing with a scenario like you see here on the right-hand side, where you have Lion loudspeakers living underneath Leo loudspeakers. And that pretty much concludes this webinar. So when loudspeakers are closely spaced together in close proximity, then delay integration becomes mission critical. Are there scenarios where you would not resort to delay integration? Sure. What if you have an MM4 as front fill? Okay, we're not gonna compromise our main PA. We're not gonna sacrifice the improved native phase response of a Lion or Leopard system to accommodate a MM4 loudspeaker. because even if they're not phase compliant at lower frequencies, the typical job description of a front fill is to add the very frequencies that are missing in the start of the audience, which are typically not low frequencies, but fresh and intelligible mid and high frequencies. So we only need the mid and high frequencies coming out of that MM4, and that allows us to get away with the fact that these loudspeakers come from different phase curve families. However, in all other instances, like shown on the screen, you would be very much advised to resort to delay integration as part of product integration. So in future webinars, we will cover the other portion of the product integration feature, which is the EQ starting point, because today we've only talked about delay integration. Let me make sure that we did everything on the list. We looked at how to name these curves according to a convention. We looked at the different curves of families. We came to the conclusion that amplitude is a control, but if amplitudes match, then phase becomes a tiebreaker. A demonstration in MAPP XT. We now understand when phase compliant matters, which is when you're in the joint custody of multiple loudspeakers, specifically coupled point sources, which are situations like outfills or downfills. Propagation delay to account for the latency inherent to different loudspeaker products, and we finished with a brief demonstration in Compass. Okay, that means that I have 2 more slides to show you. Everything that we discussed right now is also available on the Meyer Sound website. If you visit the Meyer Sound website by going to meyersound.com, you will find a video section. Hang on, I've lost my cursor. You will find a video section, and if you click on the video section, it will take you to a different page. And if you go to that page, you see all the support videos. Those for Compass, including a chapter on product integration. So all the things that we just discussed can also be found on the video section of the Meyer Sound website. Okay, that pretty much concludes this webinar. The next webinar that is coming up is a webinar on the auto splay feature in MAPP XT, which will be next Monday, March 30th at 6 o'clock Central European Time and 9 a.m. In the morning Pacific Time. We want to stay under 1 hour, so if there are any questions, a couple of questions, I'm sure that I can do the best to answer those questions. Let's see. So probably not all of us have Galaxy processors available. Will us also work on Callisto. Product integration is a feature of Compass 4.6 and Galaxy devices. So that is something that is available on those devices. There is a workaround for Callistos, but I defer to the documentation on the website for a more in-depth explanation of that. Okay, how do we sign up for the AutoSplay webinar? The same way as you did right now, because if I'm not mistaken, you completed a form and you were sent an email with the Zoom ID to join this session. If I use integration, should I use it after all tuning processes or before? I recommend to do the delay integration as first. If you know which products you're going to use on a given day, make sure that they all have the lowest common PC curve option enabled before you start calibrating the sound system. Okay, I believe we can still use all pass filters in Galileo to fix some of that stuff. Whatever floats your boat, that is beyond the scope of this particular webinar, but okay. Any other questions at this point? What causes the delay propagation? Well, that is because Leo has an analog controller card, whereas Lion has a digital controller card in that specific example. Can you use delay integration in Callisto only for the M series or Leo family? Again, I defer to the website, and please consult the more in-depth documentation. For the Lions, earlier you chose PC100, which was not the lowest. Why was this? Because the bottleneck in that example is not the Lion, it is the Leo. The lowest common phase curve available to Leo is PC100, whereas the lowest common phase curve available to the Lion is PC5570. So in that instance, it's the Leo that determines where the wraparound or phase wrap lives. Would you also add 8 milliseconds if you were not dealing with a mixed source array? That remains to be seen. That remains to be seen, because if the Lions are an outfill, without knowing where the Lions meet the Leos in space, I cannot tell you in advance how much delay it would require to make those loudspeakers arrive in time. What is really behind the phase curves? Delay integration is achieved by means of simple IIR filters. Okay. Okie dokie. The chat is slowing down, so unless you guys have any more questions, I think it's a wrap. Thank you for your attention. Thank you for your time. I see somebody asking, is there any provision for lower or beginner class aside the courses Meyer Sound offers? Well, we have an extensive training program, but due to the current state of the world, those classes which we teach in person currently cannot take place because everywhere around the world we're not allowed to gather. So for those people that struggle with this topic, yes, we offer courses which we currently cannot offer due to the world situation, but it's being looked into and see how we can address that challenge. Okay, well, stay safe and stay healthy, and for those that will be joining us on Monday next week, I'm happy to see you once more. Thank you for watching.